In this lesson, we are going to talk about conditional probability. Probabilities are calculated for a given sample space. When you know an event occurs in a certain sample space, the probability of that event will be the number of elements in that event divided by the number of elements in that sample space. But if we restrict our original sample space based on a given condition, then we can calculate the conditional probability. I will explain it using a simple example. If we look at this given contingency table, you see two different variables. In the columns, you see three cities A, B, and C. In rows, you see the gender, male and female. This table shows how 400 students are divided according to the city they live and their gender. If you look at the gender, out of the 400 students, there are 250 who are males and 150 who are females. And all these 400 students are divided so that 100 came from city A, 125 from city B, and 175 from city C. In addition to that, we see that among the 250 males, there are 50 who are from city A, 100 from city B, and another 100 from city C. So likewise, the gender, males and females, are divided among the three cities, and also the three cities A, B and C are also divided according to the gender. If you can tabulate the numbers like this for two variables, we call it a contingency table. Now we will try to calculate some probabilities. If a student is randomly selected, what is the probability that he or she is from city A? How do you calculate this probability? When we are going to select a student randomly, which means all these students have the equal possibility of being selected, we have 400 students. Among them, what is the probability that student came from city A? We see that there are 100 students coming from city A. Therefore, if we say the probability of selecting a student from city A as PA, that will be 100 divided by 400. So we see that the sample space is 400. Now let's try another one. If a student is randomly selected, what is the probability that the student is a male? Okay, let's say it is the probability student is a male. We know that there are 250 male students among the 400. Therefore, the probability will be 250 divided by 400. Now, these are general probability calculations. Now, we will try to restrict our sample space. If you select a male student randomly, what is the probability that he is from city A? Now, can you see the difference? We are not going to select a student from the whole 400 students. Now, we are selecting only out of the male students. Now, that is the restriction we are going to impose on our sample space. We restrict our original sample space now only to male students. When we restrict the sample space to male students only, we do not have to care about the female students. Now, the condition is, in our sample space, we have only male students. So, if you select among the male students only, what is the probability that he is from city A? Now, since we are selecting the male students only, we have to look at the male row only. Now, our sample space is only 250, not 400. I hope you can understand the difference between this conditional sample space. So, we write this as probability that the student is from city A, knowing that he is a male student. Now, this is how we write the conditional probability. This is the conditional probability of a student is from city A given that the person is a male. This is not the division, this is the straight line. So we read it as probability of A given male. Now let's try to find the probability. Since our sample space is now only 250, we have 50 students from city A out of 250. Now let's try another one. If you select students from A only, what is the probability that the student is a male? Now we restrict the sample space according to the city. So we look at the city A only. So we already know that the student is selected from the city A. How do we write this probability? Probability that the student is a male given that he came from city A. There are 100 students from city A. Among them there are 50 males. So this is the conditional probability of selecting a male student given that the person came from city A. Let's try to define the conditional probability. If A and B are two events in a sample space S and probability of event A is not equal to 0, the conditional probability of B given A is defined in this equation. So we read this as the probability of B given A equals the probability of their intersection divided by the given probability. See, the given condition is A. So that given event, that probability goes to the denominator. Now if you go back to the same example again and using the definition of the conditional probability to answer those questions, we'll see what will happen. So let's try to find the probability that student is from city B given that the student is a female. So that is the probability student is from city B given that the student is a female. B given female. If we apply the definition, that is the probability of their intersection, that is B and female, we divide it by probability of the given one, which is the female. Okay, so what is the probability that the person is from city B and female? Now this is a general probability, so we look at the whole sample space 400. So the probability that a selected student is from B and female is where they intersect. So here's the female line, here's the city B line. So there are 25 who are females and also from city B. So in the numerator we have 25 divided by 400. At the denominator we have the probability of female. There are 150 females out of 400. Since the denominator values cancel out, we end up with only 25 over 150. If we use the method we did earlier, when we know the sample space is restricted to females only, here's our female sample space now. We have only 150. Out of them, there are 25 from city B. So that will be probability B given female will be 25 out of 150. So you see that you get the same answer. So if you have your question in a table like this example, either you can use the table straight away and answer the questions, or you can use the formula from the definition. Here's another example. A manufacturer of airplane parts knows from past experience that the probability is 0.8 that an order will be ready for shipment on time. So it is given that the probability is 0.8 or 80%. That probability is the order will be ready for shipment on time. So let's define that probability as probability that the order is ready. Let's say probability of R, that is 0.8. We have another probability that is 0.72. That is the probability order will be ready for shipment on time and will be delivered on time. So there are two events. Okay. So we'll say R is order is ready, and D is order delivered on time. Then the 0.72 probability is the probability that the shipment is ready and it will be delivered on time. So that is the intersection. That probability is 0.72. The question is, what is the probability that such an order will be delivered on time given that it is ready for shipment on time? So how do you write that conditional probability? Probability, the order will be delivered on time, delivered given it was ready for shipment. So this is the conditional probability. Now we don't have a table-like format here. We don't have all the information, but we can use the definition of the conditional probability. So the definition is the probability of the intersection divided by the probability of the given one. So we have all these necessary numbers. Intersection is 0.72. Probability the shipment is ready for order is 0.8. So if you do this calculation, you will get 0.90 or 90%. So this is how you use the definition to calculate conditional probability. Now we have the next theorem in this chapter 2.9. If A and B are two events in sample space S and the probability of A is not equal to 0, you can find the probability of the intersection of A and B as PA times PB given A. How do you get this equation? If we write the conditional probability of B given A, that is the intersection divided by the given one. If you multiply both sides by PA, in your right hand side, PA will cancel out, and you know B intersection A is same as A intersection B. So you get probability of A intersection B equals PA times PB given A. This is called the multiplication rule. If you consider the probability of A given B, still the numerator will be same. A intersection B and B intersection A are same. The denominator will be PB. If you multiply both sides by PB, we get an alternative form of the multiplication rule. That is, the probability of A intersection B is PB times PA given B. Now these two are equivalent. Something you should remember, probability of A given B is not same as probability of B given A. They are not equal. Although the probability of A intersection B is same as probability of B intersection A, when it comes to conditional probability, you can clearly see that they are not equal. Okay, let's try another example. If we randomly select two television tubes in succession from a shipment of 240 television tubes, of which 15 are defects, what is the probability that they will both be defective? Now if we assume equal probabilities for each selection, the probability that the first tube will be a defect, since there are 240 total number of tubes and among them 15 are defectives, the probability of selecting the first is a defect will be 15 divided by 240. Now when we are going to select the second one, now assuming the sampling without replacement, which means after you select the first tube, you are not going to put it back. You keep it away. Now when you are going to pick the second tube, since we already picked one, there are only remaining 239 tubes. If we selected a defect from the first pick, now we have only 14 defects in the sample space. Therefore, the probability of selecting the second also a defect, knowing that first was also a defect, will be 14 divided by 239. Then the probability that the both will be defects will be, according to the multiplication rule, 15 over 240 times 14 over 239. So if you multiply these two, you will get 7 over 1912. So it is like, let's define the first is a defect as D1 and second is a defect as D2. The probability that the first is a defect, that is 15 over 240. This 14 over 239 is the probability that the second is a defect given that first one also a defect. So that will be 14 over 239. Now the probability that the first is defect and second is defect, so that will be PD1 times PD2 given D1. So this is exactly the multiplication rule you saw in Theorem 2.9. The answer is 7 over 1912. Here's another example. Find the probabilities of randomly drawing two aces in succession from an ordinary deck of 52 playing cards. I am sure that you are familiar with the playing cards. There are 52 playing cards in a standard deck. You know that there are 26 red cards, 26 black cards, and there are 4 suits, spades, clubs, hearts, and diamond. Now in this question, we are looking at selecting an ace. Now if you think about the standard deck of playing cards, there are 4 A's which belongs to each 4 suits. So we have the spades A, we have the clubs A, then we have the diamond A and the hearts A. We have to do the calculation to find the probability of randomly drawing 2 aces in succession. That means the first is an A, the second is also an A. In 2 situations, first without replacement, second with replacement. In order to do this example, I'll use a tree diagram. So when you are going to pick a card, either it will be an ace or not. So probability of selecting an ace or probability of not selecting an ace. Since there are 4 A's out of 52, the probability of selecting an ace will be 4 out of 52. Selecting a non-ace card will be the rest. There are 48 out of 52. Now this is the first pick. Now we move on to the second pick. So let's say this is PA1, selecting the first ace. Okay. Now we move on to the second pick. When we pick the second card, maybe the first one was an A or maybe the first is not an A. So there are 2 possibilities. So the first branch will be the probability of selecting The second is knowing that first one was also an A. So we are in the very first line. Or you may select a non-ace card, knowing that in the first pick you already had an ace. If you go to the second branch, when you pick the second ace, you may end up with a card which is an ace, but the first pick was not an ace. Or you may end up with not a card, knowing that the first one was also a not ace. Now if you multiply along these four paths, this is the multiplication rule. So the first one will be, first is an A, second is also an ace. This will be the probability. Second card is, the first is an ace. We'll write it in correct order. First is an A, but second is not an ace. This is the probability. The first card is not an ace, but the second is an A. This is the probability. First is not ace, second is not ace. So this probability, if we do without replacement, so you pick a card and you do not put it back. So if the first card is an ace, when you are going to pick the second card, the probability that it will also be an ace, that probability will be 3/51, because you picked an ace at the first place and you didn't replace it. So there are only remaining 3 aces, and in the whole deck we have only 51 cards. Okay. When you come to the next branch, what is that probability? The second is not an A, but you know that the first is an A. So there will be 48 non-A cards yet, because we haven't touched them out of 51. When it comes to third branch, the probability that the second is an ace, knowing that first one was not an A. Since we haven't touched the ace yet, when it comes to select the second one, still we have 4 a's, but the sample space is only 51. When it comes to non-ace cards, since we have already picked a non-ace card, we have only 47 out of 51. If we multiply along these paths using the multiplication rule, this probability will be 4/52 times 3/51. If you multiply along the second path, that will be 4/52 multiplied by 48/51. So likewise, you can calculate all 4 probabilities. Now according to our question, in part A, if the card is not replaced before the second card is drawn, the probability of getting 2 A's, so that is this one. Probability A1 and A2. First is also an ace, second is also an ace. That will be 4/52 times 3/51. So you'll end up with, after you do the simplification, that will be 1/221. Okay. Now if you do the same thing with replacement, now what will happen? What is the probability that first is an ace and also the second is an ace? When it comes to the first card, we know that there are 4 aces out of 52. Now you do the replacement. That means after you pick the first card, you put it back. Now when you are going to pick the second card, still you have all 4 aces and all 52 cards. So it is like the original status. So still you have 4 aces among 52 cards. So this is if the card is replaced. So each and every time you are going to pick a card, still there will be all 52 cards available, like the original status. So this will be 1 out of 169. So you can clearly see that when you pick cards with replacement and without replacement, you end up with 2 different answers. When you are doing without replacement, since the original status is restored, whatever happened in the first pick does not affect the second pick. But if you do without replacement, whatever the event happened in the first stage will affect the probability of the second stage. You can see that from this tree diagram, right? So if you select an unace card, when it comes to selecting the second ace, you can see that the probabilities are completely different. So this will be 48 over 52 times 4 over 52. So these are completely different probabilities. Now there's another thing you should understand. If you prepare a complete tree diagram like this one and multiply the probabilities along all the paths, now in this case there are 4 paths. If you calculate these probabilities, the exact probabilities, and add them together, you should end up with total probability 1. So if you add the 4 probabilities according to this multiplication rule, add these 4 probabilities together, you will end up with the total probability 1. If you cannot get the total probability 1, that means you have done a mistake somewhere in middle steps. So you can double check it. We can generalize the theorem 2.9 to incorporate more than 2 events. Now suppose you have 3 events A, B and C. Then the probability of their intersection will be probability of A times the probability of B given A times probability of C given A intersection B. Let's try to prove this one. So let's start with the left hand side, A intersection B intersection C. We will write this as A intersection B as a one component and then C. If we apply the multiplication rule, thinking that this is a one event and this is another event, you will end up with probability of A intersection B times probability of C given A intersection B. Now we can consider this as another intersection and apply the multiplication rule, which will be probability of A times probability of B given A. And we write the next statement. So we end up with the final answer. Not only for 3 events, if you have many events, still you can apply the multiplication rule. Let's try another example. Okay, in this example there is a box of fuses and there are 20 fuses which have 5 defects. You are going to select 3 fuses and random and remove it from the box in succession without replacement, which means you pick one fuse, record whether it is a defect or not, you do not put it back. Then you pick the second one, you record whether it is a defect or not, and you put it away. You are not going to put that into the bag or the box. Okay, so you are not going to replace it. So we'll say event A is the event that the first fuse is a defect, B the second is defect, C the second is defect. What is the probability that all 3 fuses are defective? So we are going to look at A intersection B intersection C. That means first is a defect and the second is defect and the third is a defect. Now we can apply theorem 2.10 here, but first we have to identify the corresponding probabilities. What is the probability that if you pick the first one, it is a defect? We know that there are 5 defects out of 20. Okay. What is the probability that the second is a defect, knowing that the first is a defect? Since we already picked a defect and you do not put it back, there are only 4 out of 90. Then we need the probability the third is a defect, knowing that first and the second were defect. What is that probability? Now you have 2 defects taken out, you haven't put it back, so there are only 3 remaining defects out of 18. So according to the theorem, this will be probability of A, probability of B given A times probability of C given A and B. We simply multiply these probabilities. Even without noting down the theorem, you can easily do this calculation by subtracting 1 from the numerator and 1 from the denominator each time. So if you do this calculation and simplify, you will end up with 1 over 114. This is the multiplication rule applied for 3 events. Okay. Now let's look at independent events. We say two events A and B are independent if the occurrence or non-occurrence of either one does not affect the probability of the occurrence of the other one. Now if we think about the previous example, when we do not replace the fuse, the probability of selecting the second fuse will depend on the previous status. If you pick a defect and do not put it back, you will end up with remaining 4 out of 19. But if you put it back, there will be still 5 out of 20. So, with replacement gives you the same original status each and every time when you are repeating. So, which means what happens in the first stage will not affect the second selection. So, those are independent events. But if you do not replace, what happens in the first pick will affect the probability of the second pick. In that case, they are not independent. We say two events A and B are independent if the probability of the B given A, the conditional probability, is same as PB. Or equivalently, the probability of A given B is same as probability of A. The explanation is the probability of B given A means the probability of event B, knowing that A has already occurred, it is same as PB, which means the given information is useless because A and B are independent. Whatever happened in the event B does not affect event A, or whatever happens in event A does not affect event B. So the given information on A is doing nothing for the probability of B because they are independent. Whatever occurred in event A, those information will not be used. Same happens here. Although you have A given B, the given information of B will not be used because they are independent. Whatever happened at event B, A is not going to affected by it. So this will remain as PA. So these two are equivalent. If that means if PB given A equals PB is true, then probability of A given B equals PA is also true. We can show that. So if we start with probability of B given A, according to the definition, this is A intersection B divided by PA. We can write A intersection B again as A given B times PB divided by PA. Now we get PA times PB given A or PB as PA given B. Okay, so which means you multiply your left hand side PB given A by this PA and divide by PB. Okay, so we end up with PA given B to be PA because PB given A is PB. We can replace PB given A by PB, and that PB and the PB at the denominator cancels out. So you end up with PA equals PA given B, right? So that is by substituting PB for PB given A in the theorem 2.9. The next definition, two events A and B are independent if and only if the probability of A intersection B is same as PA times PB. How do we get this? We know that probability of A intersection B is probability of A times probability of B given A. When A and B are independent, PB given A is same as PB. So you end up with this multiplication. So this is called the multiplication rule when A and B are independent. Then we have the next theorem, theorem 2.11. If A and B are independent, then A and not B are also independent. Okay. Suppose this is A and B. You have to show that if A and B are independent, A and B not B are also independent. Now let's split our A into two partitions. First is A intersection B. This is A intersection B. And then this is A and not B. So you can write the circle A as the union of A intersection B and A intersection not B. Since A and B are independent, by assumption, A intersection B and A intersection B prime, you can see that they are mutually exclusive. They do not overlap as the way we selected it. So we can write probability of A as the probability of A intersection B union A intersection B prime. Since they are mutually exclusive, you can split it and add the probabilities like this. Okay. Since it is given that A and B are independent, we can write A intersection B as PA times PB plus PA intersection B prime. Moreover, we can write the probability of A intersection B's prime or not B as PA subtract PA times PB. Right? So that is from reorganizing the original, the last line of the proof. Now we can take PA out. So we end up with 1 minus PB. So which is PA and not B. When you have 1 minus PB, that is the probability of B's complement. So we end up with probability of A intersection B's prime is same as PA times PB's prime. So which means A and B prime are also independent. Okay. So remember that we have if and only if. Two events A and B are independent if and only if this equation satisfies. So which means if this equation satisfies, A and B are independent. So it is both ways. And also you can extend this to many events. If you have A1, A2 up to AK independent events, and then you can find the probability of A intersection B intersection C up to the kth one by multiplying all these probabilities individually. This is when these K events are independent. Now you have to remember that 3 or more events can be pairwise independent without being independent. Okay, now we move on to the next section, which is the Bayes theorem. In many situations, the outcome of an experiment depends on what happens in various intermediate stages. Say, for example, you have the event, the student coming to the university. But in between, the students travel from home or the place the person stays to the university. Many things can happen. One is the mode of transportation. The student may come by bus, by bike, by car, or he may walk. So there are several intermediate stages for the event student coming to the university. So here's the next theorem, which is known as the rule of total probability. If the events B1, B2 up to Bk constitute a partition of the sample space S and probability of Bi not equal to 0 for all I from 1 to k, then for any other event A in S, that event, the probability of A can be calculated using this formula. This is called the rule of total probability. So the partition means, here's your sample spaces, and it has several partitions, B1, B2 up to Bk, and you select another event A. That event will also contain that partitions. So our goal is to find the probability of A. Okay, let's use an example and identify this theorem. The completion of a construction job may be delayed because of a strike. The probabilities are 0.6 that there will be a strike, and it is 0.85 that the construction job will be completed on time if there is no strike, and 0.35 that the construction job will complete on time if there is a strike. The question is, what is the probability that the construction job will be completed? It is given that the probability is 0.6 that there will be a strike. Okay, if we denote our event B as there will be a strike, then probability of B is 0.6. Okay, and it says that the construction job will be completed if that is A. It's given the conditional probability 0.85 that the job will complete if there is no strike. So that is, the job will be completed given no strike. So B is complement. That is 0.85. And also it's 0.35 that the construction job will be completed if there is a strike. So that is probability completing a job given there is a strike. That is 0.35. Okay. Now if we divide our sample space into the partitions, B is a strike, B prime is not strike. Okay. So the probability of completing the job A given there is a strike is 0.35, no strike is 0.85. Okay. The question is, what is the probability that the job will be completed on time? The job can be completed on time whether there is a strike or whether there is no strike. So which means the probability A intersection B union A intersection B prime. Okay. So this is same as probability of A intersection B plus probability of A intersection B prime. Now we have to apply the multiplication rule. A intersection B is same as PB times PA given B plus this is PB prime times PA given B prime. Now you can see that this is the law of total or the rule of total probability. If we write this is the summation. I goes from 1 to 2. We have only 2 possibilities, strike or no strike. So you have PBI times PA given BI. In our case, we can say B1 is the strike, B2 is the no strike. So you have applied the rule of total probability. And all these probabilities are provided. This will be 0.6 times 0.35 plus PB prime will be 1 minus 0.6, which is 0.4 times PA given B prime is 0.85. So if you do this calculation, you will end up with 0.55. Okay. If you want, you can use a tree diagram to answer this question also. Right? So we'll do another example and see how we can get the tree diagram. Here's another example. The members of a consulting firm rent cars from 3 rental agencies, 60% from agency 1, 30% from agency 2, 10% from agency 3. So those are the partitions. 9% of the cars from agency 1 need tune-up, 20% from agency 2 need tune-up, 6% from agency 3 need tune-up. So you have to find the probability that a randomly selected car delivered from the firm will need tune-up. Okay. So let's note down the probabilities we know. We know that the probability of selecting from the first company is 60%. Second company is 30%. Third is 10%. You can see that if you add these probabilities, you get the whole sample space. That is 100%. 60% plus 30% plus 10%. And then we have the conditional probabilities. Car need tune-up, knowing it came from the first company. It's 0.099%. Probability the car need a tune-up given that it came from the second company. That is 0.2, 20%. And then probability car need a tune-up knowing it came from the third company. That is 6%. Now we apply the rule of total probability. I goes from 1 to 3. PBI, PA given BI sum. So we have PB1 times PA given B1 plus PB2 times PA given B2 plus PB3 times PA given B3. So these are the 9%, 20%, 6%. So you will end up with 0.6 times 0.09 plus 0.3 times 0.2 plus 0.1 times 0.06, which is 0.12 if you do the simplification. So this is how you use the rule of total probability to calculate the probability of an event A, knowing that there are intermediate events or intermediate stages. Now the question comes, how do we find the probability that the car comes from rental agency 2 if that needed a tune-up? Now that is the other way around. We know that the probability the car will need a tune-up given that it came from a certain company. These probabilities we know. Now what if we need the reverse? That is the probability that the car came from agency 2 given that it needed a tune-up. And you know that B2 given A is not same as A given B2, right? So those two are different. Now how do you calculate that? In order to answer these type of calculations, we use the Bayes theorem. So that is the next theorem, 2.13. If we have B1, B2 up to Bay K, those are the partitions of a sample space S, and probability of Bi are not equal to 0, then for any event A such that PA is also not equal to 0, you can find the probability of PR given A for any R from 1 to K. You can find that by the part representing PBR in your rule of total probability. Okay, so I'll show you how you get this in the proof. The probability that BR arc partition given A. Okay, according to the conditional probability, this is A intersection BR divided by PA. Okay, so you can write this as A intersection BR by multiplying both sides. Now this is the alternative way of A intersection BR. Okay, we know that PA equals sum of I goes from 1 to K PBI times PA given BI. This is from the rule of total probability. If we replace this summation in our original equation, so the probability of BR given A, that will be intersection of A and BR, we found it is PBR times PA given BR. At the denominator you have the rule of total probability. So you end up with the Bayes theorem. Okay. Now if we go back to the previous example, if the rental car delivered to the consulting firm needs a tune-up, what is the probability that it comes from rental agency 2? So we need the probability B2 given A. So we apply the Bayes theorem. You have B2 times A given B2 at the top. We know that probability. And at the bottom we have the summation of I goes from 1 to 3 PBI times PA given BI. So if you go back to that same calculation, so at the bottom we have these values. So I'll rewrite it. 0.6 times 0.09, 0.3 times 0.2, 0.1 times 0.06, and at the bottom, at the numerator, you have out of these three, The statement corresponds to B2, which is this one. This is for B1, this was for B2, this was for B3, and you pick the B2. Right? So if you do that, you will end up with 0.06 at the top, 0.120 at the bottom. So the answer will be 0.5. Now if you need the probability B1 given A, what do? You pick the statement or the part correspond to B1 to the top and use all three at the bottom. If you need probability B3 given A, you pick the part belongs to B3 to the top, divide by all three. So this is very easy. Let's look at another example. In a certain state, 25% of all cars emit excessive amounts of pollutants. If the probability is 0.99 that a car emitting excessive amount of pollutants will fail the state emission test, and the probability is 0.17 that a car not emitting excessive amount of pollutants will nevertheless fail the test, we have to find the probability that a car fails the test actually emits excessive amounts of pollutants. Now in this question you can see two different events. The first one is emitting pollutants, the second is failing the emitting test. Let's use a tree diagram to answer this question. So the first level of the diagram is about emitting the pollutants. It says that 25% of all cars emit excessive amount of pollutants. So there are cars who emit pollutants and there are cars who do not emit pollutants. So let's say the first branch as emitting pollutants, that probability PA is 0.25. The rest of the vehicles do not, so let's say PA not. Since you have 25% of cars emitting pollutants, the rest will be 1 minus 0.25, which is 0.75. If you add the probabilities in these two branches, they should add up to 1. Then we have the conditional probabilities. The probability is 0.99 or 99% that a car emitting excessive amount of pollutants will fail the state emission test. So we are here where the vehicle emits pollutants. If it emits pollutants, the probability that it will fail the test. So let's say probability of B failing the test knowing that it is a pollutant. So that probability is 0.99. The others will pass the test. So let's say B prime knowing A. Since you have 99% failing the test, the rest will pass the test. That will be 0.01. So altogether this will be 100%. Then we move on to the next one, the next level where the vehicle does not emit pollutants. It says that the probability is 0.17 that a car not emitting excessive amount of pollutants will nevertheless fail the test. So the probability of failing the test knowing that the vehicle does not emit pollutants, that probability is 0.17. So the rest will be not failing or the passing the test, given that the vehicle does not emit pollutants. 1 minus 0.17 is 0.83. Now if we multiply along each of these four parts using the multiplication rule, the first one will be the probability A and B, that is the car emits pollutants and failing the test. So that will be 0.25 times 0.99. The next branch, probability the car emits pollutant and pass the test, that will be 0.25 times 0.01. So likewise you can fill the other two branches. So this will be A prime and B, 0.75 times 0.17. And finally probability A prime and B prime, which is 0.75 times 0.83. If you multiply these four values and finally add them together, you should get total probability 1. But what we need is only the probability that the car that fails the test actually emit excessive amount of pollutant. So the probability we need is probability A given B. So again it is the probability that the car fails the test actually emits excessive amount of pollutant. So you already know that car fails the test, so it is given B, and it actually emitting pollutants is the probability of A. So what you need is the probability of A given B. You don't see that probability in the tree diagram. What we see is B given A, but they are not the same. So you can apply the Bayes theorem here. At the denominator, you have the rule of total probability, which is PA times PB given A plus PA prime times PB given A prime. Out of that, what you need is PA given A times PB given A. So that will be probability of A intersection B divided by PB. Okay, so I'll show you how to get this one even without using the Bayes theorem. You can see that the probability of A intersection B is here in the very first branch, which is 0.25 times 0.99. The probability of B, you can see the two probabilities in the intersection where you see the letter B. That will be the first one and the third one. So you have to add these two to get PB. That is the rule of total probability. So at the bottom, PB can be gained by PA intersection B plus PA prime intersection B. So this is the same thing written in two different ways. So you have 0.25 times 0.99 at the top divided by the first one, again 0.25 divided by 0.99 plus the third one 0.75 times 0.17. So if you do that calculation, you'll see the answer will be 0.66. Okay, here's the last example. There are 4 cashiers at a supermarket and a survey was done to measure the satisfaction of customers at checkout about the service on these 4 cashiers. It is given that 75%, 80%, 90% and 95% of customers said they are satisfied on the service provided by each cashier A, B, C and D. So that means 75% is the probability that the customer said the service is good, knowing that it is for the first cashier. 80% is that the customer is satisfied given that he got the service from cashier B. So these 4 are conditional probabilities. It is given that selecting a cashier at checkout is equally likely for all 4 cashiers. You have to answer the given probabilities. Again, we'll start with the tree diagram. Now in this case, the 2 levels will be selecting the cashier and the next level will be the satisfaction. Since there are 4 cashiers, we start with 4 branches in the first level. We have cashiers A, B and C. So we have the probability of A, probability of B, probability of C, and probability of D. For each cashier, the customer will say whether they are satisfied or not. So the next level will be satisfied, knowing that the service got from cashier A. Probability not satisfied, knowing that the service was from cashier A. So likewise, for all 4 cashiers, you get either satisfaction or not. So you can fill all the branches like this for all 4 cashiers. So at the end, you will end up with 4 times each having 2. There will be 8 branches or 8 paths at the end. Now we'll try to find the probabilities. We know that the customer is satisfied given that they got the service from cashier A is 75%. Then not satisfied will be the rest, minus 0.75, which is 0.25. Cashier B, it is 0.8. So this will be 0.2. For cashier C, it is 90%, and for D, 95%. So not satisfied is 0.1 and 0.5. Now we need the probability of selecting each cashier. How do we find that? It says that selecting a cashier at checkout is equally likely. That means all 4 cashiers have the same chance of being selected. Since the total probability is 1, if you divide 1 by 4, each will get 1 over 4, or which is 25%. So all of them have the equal chance of being selected. Now you have to multiply along these 8 paths to get the intersection, which is the multiplication rule. So we'll see what do we get. This is the probability the customer got the service from A and satisfied, which will be 0.25 times 0.75. That will give you 0.1875. Then service from A and not satisfied, 0.25 times 0.25, which is 0.0625. So likewise, we will fill the rest. This is the probability. B and satisfied, B and not satisfied, 0.25 times 0.8. Answer will be 0.2. Then 0.25 times 0.2. Answer is 0.05. Then we go to the cashier C. Satisfied, not satisfied. We can do the multiplication and the answer will be 0.225 and 0.025. For the last one, service from cashier D and satisfied, you will get 0.2375. Finally, D and not satisfied, probability is 0.0125. So as I mentioned earlier, if you add all these 8 probabilities, it should be the total probability 1. So you can double check your calculations. When you have a tree diagram with all these probabilities, it is very easy to answer questions like this. The first one is the probability that the customer is satisfied. That means you have to find probability S. Okay, so if you go over these intersections, you see the probabilities where you have S So you have that in 4 places. So that will be satisfied from A, satisfied from B, from C, and from D. So you have to add all these 4 probabilities. A and satisfied. This is actually the rule of total probability. B and S, C and S, finally D and S. So these probabilities will be 0.1875 plus 2 plus 0.2250 plus 0.2375. So the answer will be 0.85. Next question is the probability the customer is not satisfied. You can find the answer using 2 ways. Either you add up the probabilities where you see NS, so this one plus this one, 4 probabilities, or the easiest way is satisfied and not satisfied, they are the complements of each other. So probability not satisfied will be 1 minus probability satisfied. You already have PS, so 1 minus PS is 1 minus 0.85, which is 0.15. So if you want to double check this answer, you can add these 4 probabilities and check whether you can get 0.15. So that was part 2. Then we have to find the probability of A given customer is satisfied. 3. Probability A given customer is satisfied. So what is that probability? That is the probability that the service was taken by A knowing that the customer is satisfied. So if we apply the conditional probability, this is the probability A and S divided by probability of S. So the probability of A and S, you see it here at the very first line. So that is 0.1875. So you have 0.1875 divided by PS. PS you already have it. This is the denominator of the Bayes theorem. So you have already found the answer 0.85. So that is 0.1875 divided by 0.85. So you can find that answer. The last one, probability the cashier is D given customer is not satisfied. That is the probability that the customer got the service from cashier D knowing that the customer was not satisfied. Again, we'll apply the conditional probability, the definition, divided by probability of NS. Again, we can find D and NS. Here's the intersection. That is 0.0125. See, it's the very last line, 0.0125. Divide by probability of NS, and we have already got the answer in part 2, which is 0.15. So you can find these answers very easily.